Alright, today's video is going to be two separate videos actually. The first video we're going to finish up this section 4.1, which is our introduction to flexural members. This section we're gonna end this section with the derivation of our bending stress equation, and then in section 4.2, our next video, we will use that derivation of that equation and we'll work out our first example problem for bending stress. So up till now, everything in the class has been axial stress, axial deformations, longitudinal strain, longitudinal stress. Everything's been in that axial longitudinal direction, but now we're going to swap our thinking up. We're going to switch it up, and we're going to be looking at flexural members now, things that are actually bending. So in class on Tuesday, we started section 4.1, where we had this, this rectangular beam before and after deformation, and we bent this into, we applied these end moments to this beam and forced this beam into like a smiley face bending orientation. The key takeaways was that the top was in compression, and that the bottom was in tension, the way that we bend this out. Okay, so we went over all this in class on Thursday, or I'm sorry, on Tuesday, and we came to this conclusion. Then we took a slice out of our beam here, that were our hypothetical beam. We took this slice out, plucked it out, drew a free body diagram of it here, and basically came up with the equation that the strain of this red line, right, the strain of this red line was negative y over rho, right, rho being the radius of curvature of the bending beam. We said that this told us two things. One, this equation tells us that maximum strains occur at top and bottom of the beam. Right? That makes sense, because y in this equation, with strain equaling negative y over rho, rho is constant, so y is the only variable. So as y gets bigger, strain will get bigger, and y is the distance from the neutral axis, which was labeled, here, our neutral axis. All right. So if we're going towards the top of the beam, we get a positive y, which means we'll get a negative strain. And if we swap around and go down from the neutral axis, we will have a negative y value, which will make our strain positive, meaning just tensile strain on the bottom, compressive strain on the top, which makes sense because that's what we've said we're going to have with this beam bending orientation. Okay, so first thing was that our maximum strains occur at the top and the bottom. And our second observation that we made from that equation is that our strain varies linearly with distance from the neutral axis, right? It's just a linear function. So the further away we get, if we're X amount of distance away from the neutral axis, we get some strain, and if we're 2 times that, we get twice that strain, right? So it's just a linear function with distance from the neutral axis. Knowing this, then, what we can do is come up with a equation then in terms of y for what strain is at any point y, and this is what this little picture on the right represents. So if our strain max, if our maximum strain is at the top here, and y is our distance from the neutral axis, and c is the distance from the neutral axis to the top of the beam, then our equation for what strain is anywhere along the height of the cross section can be represented by this equation here, where we say it's negative y over c times strain max. All right, that's an equation. It's just a mathematical equation of what we have found out thus far, right? We get a maximum strain top and bottom, and it varies linearly. Just putting that into an equation format, we get this equation where strain equals negative y over c times strain max. All right, so let's take that equation that we've just come up with, this y over c times strain max, and let's take that and let's apply Hooke's law to this formula. All right, so if we have strain equals negative y over c times strain max, and we apply Hooke's law to it, Hooke's law states that sigma equals E epsilon, right? So just solving for epsilon, what we find, just applying Hooke's law to this, is that sigma over E is equal to negative y over c times a variable that we're going to call sigma max over E, right? So strain epsilon gives us sigma, epsilon max gives us sigma max when we apply Hooke's law to this. So looking at this equation, we see that we have the modulus of elasticity E in the bottom of in the denominator of each side of this equation. So our modulus cancels out, and what we're left with is sigma equals negative y over c times sigma max. Now this equation looks very similar to the strain equation right above it. All we've done here is just substitute a strain for sigma, and what that tells us then, it tells us the exact same two things that we figured out with the strain. So it tells us the same two things about the stress profile, right? Stress is maximum at the top and bottom of the beam. And it also tells us that stress varies linearly across the cross section. All right, so stress varies linearly, again with distance from the neutral axis. All right, so summing this up into picture format here is I've got the strain profile, right? So the strain profile is on the left and the stress profile is on the right. Okay, so for this particular beam that we're doing our derivation on, we've applied the end moments such that the top of this beam will be in compression. It's smiley face bending. The bottom will be in tension. So the x-axis here represents that neutral axis, right? That point somewhere in the middle of the cross section where we have no strain, because we have to, if we've got negative strain at the top of the beam and positive strain at the bottom of the beam, stands to reason that somewhere in the middle we've got no strain, and that's right here at this x-axis, which we called that the neutral axis. Neutral axis is where there is no stress or strain. So strain profile on the left and stress profile on the right. What you'll see here is that we get negative strains on the top, which means it is a compressive strain, and we also get compressive stress from those compressive strains, right? That makes sense. Same thing on the bottom of the beam, where we have positive strains, we get positive stress, which just our general sign convention, we have always assumed that positive is tension and negative is compression, right? So we get compressive stress on the top of the beam, we get tensile stress on the bottom of the beam, and the maximum values will be, the maximum compressive stress will be at the very top of the beam, the maximum tensile stress will be at the very bottom of the beam. At the neutral axis, we have no stress, which makes sense because we have no strain. And so that occurs at the neutral axis. Also, the stress profile is linear, so just if we needed to find the stress what the stress is at any point y on the cross section, we just plug in into our equation of sigma equals negative y over c times sigma max. Okay, so those are our two equations up to this point, but the problem with our derivation at this point is that we don't know numerically what this sigma max value is, right? We can take our beam profile and we can calculate up y and c, but we don't know what sigma max is yet. So let's take a look at another free body diagram and see if we can't figure out what this sigma max variable is going to equal. So let's take this free body diagram where we've cut this beam, and it is a free body diagram, right? So assuming that the beam itself was in equilibrium, we've taken this free body diagram of it. This free body diagram must also be in equilibrium. So applying our equations of equilibrium to this free body diagram, we're going to be able to do some things. So let's take this our first step here, and let's sum forces in the x direction. X direction is the longitudinal axis of the beam. So if I take my free body diagram here and I sum forces in the x direction, what I'm essentially going to be doing is imagining that that the stress profile itself is comprised of all of an infinite number of these little bitty dF forces that act over these little bitty dA areas, okay? So anything above the neutral axis, this Z axis in this picture is the neutral axis. Anything above the neutral axis will be a compressive stress, which on our free body diagram here is pointing in the negative x direction. And then anything on the bottom or below the neutral axis, so this will be compression on the top, this will be tension on the bottom. All of these little forces, a stress profile is nothing more than just an infinite number of little forces acting together. So if I'm going to sum forces in the x direction, what I need to do is sum up the stress profile. So basically sum up all these little dF forces. So in equation format, what this is going to look like is we're just going to have to do an integral, right? Because the stress profile coincides with the shape of the beam, right, itself. If it's an I-beam or a rectangular beam or a circular beam, it doesn't matter. But the stress profile depends on the shape of the beam. So what this ends up being is the integral over the cross-sectional area A of just all these little bitty forces, all of the little dF forces. So if we know, if we're going to integrate dF, but we need to have some sort of variable for our integration, right? So we need to have like a dA or something. If we know that sigma is equal to F over A, then we can say then that F equals sigma times A, right? And just taking that, we're going to plug that in for dF, and what we get here when we do that is that the integral over A of dF is integral over A of sigma dA, and then plugging in then we have an equation for sigma. So we get integral of a of negative y over c times sigma max dA. Okay? Just plugging in this equation that we have already come up with sigma, plugging that into our integral now, and we're left with this. What this tells us is that sigma max is a constant and c is a constant. Y is the only variable. So let's pull the constants out of the integral and see what we're left with. We get negative sigma max over c times integral over the area of y times dA. Okay? And we know, since we're summing forces in the x direction, and then we know this must be in equilibrium, right? We can set this equal to 0 because it's got to be in equilibrium. So looking at this equation here, I've got one term of negative sigma max over c, and I've got the other term of integral over a times y dA. All right, when we take these two terms and multiply them together, they've got to equal 0. So mathematically, we know that one of these two terms has to equal 0 for this equation to be satisfied. But the thing is that negative sigma max over c, those are actually just two numbers. They're never going to be 0. So that tells us that the integral over a times y dA must equal 0, right? So writing this out, we'll say since negative sigma max over c cannot equal 0, right? Because these are just two numbers. These are two real numbers, 17 divided by 3 or something, right? They'll never equal 0. They are non-zero numbers. So since that term cannot be 0, we find that the integral of a of y times dA must equal 0. Okay? So that's what that equation tells us. Knowing that it has to be in equilibrium, that the term of the integral term of the equation must equal 0. Now, another point to make on this equation, this derivation right here, is that if you guys may recall from your statics, if anybody's got any statics nerds out there, what we find, if we can recall from our centroid equation, is that our centroid equation is integral over area times y dA over integral over the area dA. Okay? So let's just recall that the centroid equation is that. Now looking at our bending stress, our sum forces in the x direction, we find that the numerator of our centroid equation, this integral y dA, is the integral term in our equation that must equal 0. All right. So what does that tell us then? It tells us that y bar must equal 0. And if y bar must equal 0, what this whole equation tells us, what the whole purpose of this exercise is to tell us is that our neutral axis, because all of our neutral axis is depending on where y is, right? Because this is the neutral axis, this is our variable y. Y is the distance from the neutral axis. So wherever we put that coordinate system, our y bar has to equal 0. What this tells us mathematically then is that our neutral axis coincides with the centroidal axis. Which is huge, right? Our neutral axis is now not just some arbitrary point on the cross section. We now know mathematically that our neutral axis coincides with our centroidal axis, and we've been doing that all the way up to this point in this semester, where we've been calculating where the centroid of a shape is. All right, so this is big. this is why we need to know how to calculate centroids, because the centroid of a cross section is where the neutral axis is, and it's our starting point for our bending stress equations, right? This will be the point where we have no stress or no strain. So this is our starting point. This is the neutral axis. This is our centroid right here. This is the centroid right here. If you can calculate the centroid, you found the neutral axis, which gives you your starting point for being able to calculate all your stresses. All right, so that's great. We summed forces in the x direction on this free body diagram, but that doesn't mean it's actually in equilibrium. We still have to sum forces in the y direction and take a moment somewhere, right? So looking at our free body diagram, there's no forces in the y direction, so we're not going to actually sum forces in the y. All we've got left is we're going to take moments, okay? And on this free body diagram, if we take moments, we're going to take moments about the z-axis, really. We're going to take moments about the neutral axis, which is the z-axis. So let's do that and see what this equation tells us when we're going through that. So step 2, we're going to sum moments about the neutral axis. And what we have here is we have the moment created by the stress profile. So if you can imagine the stress above the neutral axis is compressive stress, right? And it's pointing in the negative x direction. And below the neutral axis, we have a tensile stress, and it's creating forces in the positive x direction. But if we were to take the moment from the entire stress profile itself, you will see, hopefully, that stress profile creates, on paper right here, what I would consider to be a clockwise rotation about the z-axis, right? You've got the forces on the top that are pushing back in the negative x. You've got the forces on the bottom that are pushing in the positive x direction. Both of those forces added together will create rotation about the z-axis, which means that we're getting a moment about the z-axis from there. So those will have a moment from the stresses, and then also we have just the plain applied moment that we have on this free body diagram as well, just the m, okay? So if I sum sum moments about the neutral axis, what we get is that we have the moment m itself, right? And then we're going to take the moment from the stress profile, right? And we're still going to have to do this in integral form, and taking the moment of all of these little df forces is essentially what we're doing. What the moment is going to be is it's going to be df times y, right? So y is the location vertically of df. So the moment of that force about the z-axis is going to be df times y. We just have to take that moment, df times y, do it for every little bitty, infinite number of df's that we have. So integral form, what we get is minus integral y df over the area. Okay. Again, this is a equilibrium equation. We know this must equal 0. So just rearranging this, we find that moment is equal to integral over the area times y df, but we know that df is again sigma times dA. And once more, just substituting the same variables that we have been working with this whole time. Moment is equal to the integral then over the area y times sigma, sigma being negative y over c times sigma max times dA. And again, pulling the constants out of our integral, we have moment equals negative sigma max over c integral a y squared dA. All right, so we're left with this equation right here. if you will recall from statics, again, this is very similar as up here when we were summing forces in the x direction, where we had the integral over the area of y times dA must equal 0, and that was the centroid equation. This equation right here, the integral over a y squared dA, again recalling from statics, this is the moment of inertia of our cross section. Okay, so if integral over a y squared dA is just the moment of inertia I, what we find then when we rearrange this equation, we get sigma max equals negative mc over I. Okay, that's huge. That's our equation. Sigma max is negative mc over I. And then finally, if we wanted to, so looking at our stress profile on the page before, sigma max equals negative mc over I. Okay, sigma at this point here, right, just rewriting this if I wanted to. If I wanted to figure out what the stress was at this point right here, or I'm sorry, let's just put it over here at this point, y. So maybe at this point, sigma at this point just becomes negative my over I, right? So mc over I is the maximum, and then if you wanted to know what the stress is at any point y from the neutral axis, you just plug in y instead of c, you get negative my over I. Okay? So we'll put that here, or sigma at any point is equal to negative my over I. Okay? Only difference between the mc over I and the my over I is c is a specific point, which is the top or bottom of the beam, right? It can be top or bottom. All right. This is the bending stress equation, these mc over i's, right? My over I, mc over I. These are the bending stress equations. So when I ask you, or whenever you're asked to find the bending stress, what is the bending stress at this point along the beam, you're going to come in and use this equation, mc over I. All right. Let's talk about what these variables are. I is the moment of inertia in the direction that's getting bent, correct? C and Y, those are just distances from the neutral axis. M, however, is, I want to make this note, right? This M in this equation, the mc over I or the my over I equation, they're the same thing. The M, I want you guys to understand this. It's a huge point. Is the internal moment, right? It's not an external moment. It's not some moment that gets applied to the beam or whatever. This is the internal moment, okay? So how do we find internal moments? We find those from the shear moment diagrams, correct? We have a beam, and then we draw our shear moment diagrams. The value of the moment along the length of the beam, that is what goes into this equation, right? It is the internal moment. Internal moment times whatever distance you're looking at divided by a moment of inertia will give you a bending stress, okay? So that's going to wrap up this first video. This is just the derivation of our basic bending stress equation, mc over I. All right, sigma equals mc over I, negative mc over I. The negative sign just denotes whether it's going to come out to be a compressive stress or a tensile stress. But the variables are just mc and I. Okay, in the next video, we're going to cover section 4.2, where we basically do an all encompassing example over bending stress so that we can understand how this equation works on actual beams. So that's it for this video.